In this section, we're going to be talking about area, but before we can do that, we need to introduce sigma notation. So that's what this video is going to be about. So sigma notation uses this symbol that looks kind of like an uppercase E, but it's actually a Greek letter uppercase sigma. And it says the sum of n terms a sub 1 through a sub n is written as the sum from I equals 1 to n of a sub I. So that's the sum from I equals 1 to n of a sub I. And that's going to be a sub 1 plus a sub 2 all the way down to a sub n. Now, I is what we call the index of summation, and a sub I is what we call the ith term in the sum. The upper and lower bounds of summation are n and 1, so the sum is going to go from I equals 1 to I equals n. So, for example, if I want to add the first 6 terms of the series I, for I equals 1 to I equals 6, I'm just going to plug the I into the formula for each term. So that's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6, which you find out turns out to be 21. Now for this one, I've got the sum from 1 to 3. So we've got I equals 1, I equals 2, and I equals 3. But in this case, the formula for each term is I plus 1, so this will be 1 plus 1. This will be 2 plus 1, and this will be 3 plus 1. So this is 2 plus 3 plus 4, which is 9. And in this one, I'm looking at the first 4 terms. So from I equals 1 to I equals 4. And I'm going to have 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 which is 2 plus 4 plus 6 plus 8, which is 20. Now we have 2 properties which come from the associative and commutative properties of addition and the distributive property. So if k is a constant, the sum from 1 to n of k times a sub I is equal to the constant k times the sum of a sub i's. And if you're adding or subtracting your terms, you can also just add or subtract the sums individually. The other formulas that we have that are going to be very important are these right here. And so this is saying that the sum from 1 to n of a constant c is just c times n. That makes sense, right? Because you're adding c to itself n times. The sum from 1 to n of I is n times n plus 1 over 2. And the sum from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And the sum from 1 to n of I cubed is n squared times n plus 1 squared over 4. So if anyone ever picks on you and asks you to quickly add the first 100 natural numbers from 1 to 100 of adding them together, this would be 100 times 101 divided by 2, which is going to be 5,050. So you can do it in your head without having to actually add them all together in your head. Now the way that we're going to use this in the next 2 sections is as follows. We've got a summation from 1 to n of I plus 1 over n squared. Now this is very important. This is a form for the ith term. So any variable other than I in this expression right here is actually going to be treated as a constant. So I can use this rule that we had earlier that said I could bring out constants, and I could go ahead and make this 1 over n squared times the sum from I equals 1 to n of I plus 1. And I could split that up into 2 different sums. So I'd have the sum from I equals 1 to n of I plus the sum from I equals 1 to n of 1. And we know that the sum from 1 to n of I is n times n plus 1 over 2. And we know that since this is a constant, c, this would be 1 times n. So if I were to do a little bit of work on this and clean it up, find a common denominator and all that sort of stuff, I would end up with n squared plus n plus 2n all over 2. or 3n squared plus n over 2n squared if I bring in the constant. And then I could factor out an n, which will give me, actually scratch that. I would have n squared plus 3n over 2n squared. And if I factor the n out, I can actually cancel one of the n's. So I get n plus 3 over 2n. Now this gives me a closed formula for this sum, so meaning instead of having to actually plug in however many values of n that I want and add them all together, I could just plug whatever the n is into this and get an answer.